Hello and welcome to my talk about eBPF and Kubernetes, where eBPF came from, how it's developed today and what it brings for the future, and how it relates to Kubernetes, and taking one example here of how it can scale Kubernetes services. I'm Daniel Borkmann, and I'm one of the two eBPF co-maintainers in the Linux kernel. So let's dive right in. Kubernetes is basically eating the world today. More and more enterprises are moving over to containers, and basically Kubernetes is regarded as the cloud OS these days. And underneath all of that, there's the Linux kernel as a base foundation to provide all the building blocks for Kubernetes itself, but also for the containers in terms of, for example, C groups, network namespaces. In some of the core critical parts for those deployments, they are delivered through a so-called CNI networking plugin, if we take the networking angle as an example. So what does this CNI plugin in Kubernetes do? Basically, it provides general pod connectivity. And that means when Kubernetes is basically spawning a new pod, that CNI plugin is then creating network devices, moving them into the new network namespaces, and also assigning IP addresses, routing, and so on. Basically, it manages even several IP addresses, an IP address pool. And some of the CNI plugins also take over Kubernetes service handling, in that they provide load balancing for services, and as well as network policies. Given all that can be quite complex, they also offer monitoring and troubleshooting on top of all that. And today we're seeing two clear trends. One is the pod density is increasing for a given Kubernetes node. That means people are running more and more pods on the same node. And the other one is decreasing the pod lifespan, even down to seconds or a fraction of seconds for their workloads. There are some interesting user survey reports that also back up this data. There are challenges from the operating system kernel side, of course, with that, because the Linux kernel, or in general the kernel, has to keep up with all the performance and scalability requirements that users have in their data center, as well as the increasing complexity of kernel subsystems. One issue with that is that Linux kernel is not allowed to break user space. That's of course a good thing, but that also means that we have to keep all the old legacy from 5 or 10 years ago around and keep it functioning so that we keep applications working. And that, of course, makes the kernel more complex, and it can affect the fast path as well. It means that the kernel often suffers a feature creeping, you can call it feature creeping, normality. What does it mean? Well, users add, or developers add more and more features to the Linux kernel. It becomes more complex, and nobody is potentially able to understand all of those. There's actually an interesting definition on creeping normality on Wikipedia even. And it's defined as a process by which a major change that would otherwise be rejected when proposed as is can be accepted as normal or seen as acceptable if it happens through small and incremental, unnoticeable changes. And there's actually an interesting quote on that from Linus Torvalds on crazy new features for the kernel. He says he can work with crazy people, it's not a problem, but they need to sell their crazy stuff with non-crazy rational arguments in small, well-defined pieces. So when he's asking for killer features, he wants actually those developers to log him into a safe and cozy world where the stuff that they are pushing is useful for core kernel developers first. In other words, like those crazy features should be wrapped as a Trojan horse. They should look obviously good at first sight. And that's pretty much what happened to eBPF back in the days when it first got merged. So it's a crazy new kernel feature, but in the long term for the Linux kernel, it actually reduces the kernel's feature creeping normality, because all the weird corner cases that users have and ask from the kernel, instead of having them hard coded in the kernel and potentially in the kernel's fast path, they can instead live inside an eBPF program where no one else has to suffer from potential performance degradations, meaning it allows to keep the kernel's fast path fast. And also it allows to make the kernel fully and safely programmable, so users won't crash the kernel. And eBPF has been designed to solve real-world production issues, and it still is with that in mind today. How does it look like? eBPF is defined, or can be written in a C-like language, and that can, for example, either be generated or managed by another user space application or agent. In our case here, Cilium is one example. Cilium is a Kubernetes CNI, what I mentioned earlier. And that program gets compiled through a compiler, in that case, the LLVM compiler suite, and it can generate a BPF object file. And that object file is being handled by a BPF loader, where it creates all the necessary steps and pieces to load it into the kernel, those BPF instructions that have been generated, and they are passing inside the kernel through a BPF verifier, which makes sure that, for example, memory access is not happening out of bounds. It cannot crash it or loop forever or all these sort of things. And once it determined that the program is safe, it will be just-in-time compiled in order to generate native code that can be run on the underlying architecture, for example, x86. And in order to share state, BPF programs can use so-called BPF maps. Those are shared storage that is accessible from BPF program side, but also from the user space side. And BPF needs to be triggered through an event. And in case of networking, which is the example here, that event is of course a network packet. So a network packet basically triggers the execution of the BPF program. The BPF program can mangle the packet, it can forward it, and in the end, it returns a verdict. So aside from forwarding, what is also supported is dropping or pushing it up the stack and so on. And the crucial part in all of that is, again, that it cannot crash the kernel. It is as fast as a kernel module, and it provides stable API guarantees. So what does that mean? It basically means that when a BPF program keeps working on an old kernel version, it will also continue to keep working on a new kernel version without having to change the program itself. It's similar to user space, like the contract that the kernel has to user space, where we don't break applications and kernel updates. And this similar thing is happening for the eBPF world, for example, for the networking case. How does the packet flow look like in the traditional case of Kubernetes, where it's using the kube proxy component in order to handle Kubernetes services? What you can see here is that packets coming from a NIC are entering the stack. The Linux kernel is creating a packet representation called SKB. Then it's like pushing this the packet to the traffic control ingress hook, and then all these orange boxes are net filter IP tables related. So there's pre-routing hooks. Then there's the actual routing lookup. It determines that the packet needs to be forwarded to a different networking device. Then there are those post-routing hooks. Again, TC egress one. And then it can determine that the program has to go to a local pod. Then it will forward it to a local weave device, for example, or a local service endpoint. Or it will go back out of the node if the packet is destined at a remote service endpoint on a different node. It can be the same network interface or a different one. So the same packet flow under eBPF, for example, when used with Cilium, looks quite different in the sense that a lot of the overhead and orange boxes can be avoided simply by pushing the packet from the TC ingress write to the TC egress hook and then forwarding it that way. So Cilium would allow, together with the eBPF, with its eBPF data path, to accomplish that. And it can even go crazier than that in the sense that you could forward those packets to remote service endpoints at the XDP layer. That XDP box is basically called the express data path, and it allows for running BPF programs inside the driver layer and forwarding them directly from there without having to push it up the stack. So we can save all the additional overhead and be super fast. So how did it look in the very early days of BPF? So basically, we're speaking about pre-2013. You can consider it as the SDN landscape for Linux at the time, if you will. So back in the days, there was Open vSwitch project, or called OVS, the traffic control, and also the NetFilter subsystem, consisting of, for example, IP tables, IPVS, NF tables was there back then. And those allowed you to, let's say, program the data path. BPF back then was used for TCP-dump to filter network packets inside the kernel as early as possible and without crashing it. And it was also used for seccomp in order to do system call filtering, but its use was very limited and also constrained. Not the same as we have today with the eBPF. There was also a feature creep and often also code duplication between TC and NetFilter because both subsystems were sort of competing with each other. And Open vSwitch back then was considered like the most advanced data plane in the networking stack, but it didn't integrate well with networking, and it was also considered as a sort of a Frankenstein by other core developers. So yeah, so how does it compare? Those subsystems still exist today, so how do they compare to eBPF? You can think of it this way, that Open vSwitch, TC, and NetFilter, they allow you to program the data path, but only if the data path knows what you want to do, only if those concrete building blocks are in the kernel as code. And eBPF instead lets you freely create that data path instead, because you provide everything through a BPF program. So the extended BPF, that initial first patch set was presented by Alexis Reutov back in the days in 2013 as a big patch bump. It was like, caused plenty of discussions, but it was considered too intrusive. Back then also NF tables was sort of on the rise. It was inspired by the old BPF that TCP-dump had, and people weren't quite happy because it would, like that patch set would add another BPF interpreter, so two would have to be maintained. It was sort of a hurdle, and it eventually got rejected. So you can see that here that the Linux crazy rule on new kernel features applied that I mentioned earlier. You need to chunk it up into small incremental pieces to give a safe and cozy world. And in 2014, basically, we reworked the whole patch set and made it mergeable, and it also got merged into the kernel. So that's like the initial code on eBPF that we had. And what it did, it was basically replacing the old BPF interpreter entirely. So the kernel wouldn't have the old TCP-dump anymore, but instead the new eBPF one. And the instruction set got heavily extended, and the TCP-dump BPF language back then got translated inside the kernel to the new representation, and later also the verifier and JIT pieces got added and much more work on top of that. And we basically, Lexi and myself basically became maintainers because we spent most of the time hacking on working on BPF and the kernel and overseeing the development since then. That's where it happened, basically, where David Miller, the networking kernel maintainer, applied the patch set. And yeah, thanks a lot for that. And what else happened in that year? Actually, it's quite interesting. 2014, also the first Kubernetes patch went public. So in 2015, the development of eBPF moved into two directions, networking and tracing. And a major milestone that is still the base foundation for all the work is that the BPF backend got merged into upstream LLVM, into the compiler suite. So that you were able to compile the C code into BPF instructions. And the first patch set, so Alexei worked mostly focused on tracing back in the day, and he added the patch set to allow to attach eBPF to tracing to allow for system observability. And I was mostly focusing on networking and made the TC subsystem programmable through eBPF in order to have a networking data path that is flexible and also fast. We also made the TC lockless so that it would be fast without any CPU contention, and also add next to an existing ingress also an egress hook. So you have both attachment points to see all the traffic. Yeah, so there was plenty of other work on top of that. And back in 2015, the BCC project first got announced. That is a tracing front end and used by many people today to get introspection to the system and solve production issues. In 2016, there was another major milestone on the networking side. The express data path, also in short XDP, got merged, and that basically allowed to attach BPF programs into the driver's ingress layer without having to go up into the stack. And also, like, the first networking card came up and driver that was merged that would allow for offloading BPF programs. The Cilium project was first announced in 2016 as well. It was built for container networking. And back then, mainly targeted for Docker because Kubernetes was still in the very early days and not as heavily used as today. And it would allow for efficient label-based policy, NAT64, you would be able to create tunnel meshes with VXLAN and Geneve, and basically have an eBPF-based data plane. The whole data plane forwarding happens through eBPF and no more Docker or OVS bridge devices and so on. So that could be avoided entirely. 2016-17 was basically the year where eBPF began taking over production environments, which is really exciting. Brandon Gregg from Netflix called out the Linux BPF superpowers. He's been working on tracing heavily on creating the necessary needed tools for the BCC project. And he says it's compared to the dtrace, where he has like 13 years of experience, eBPF is worth way more and exciting, even though just in this short time span, the capabilities are staggering. And Facebook announced that they were replacing their, at that time, existing IPVS load balancing infrastructure over, and they migrated away from NetFilter entirely to eBPF. And they were attaching those programs to the XDP hook in order to do layer 4 load balancing and DDoS protection. And since 2017, every packet that goes to facebook.com basically passes through XDP and eBPF. So it really is battle tested. Cloudflare basically also saw that potential, and they migrated from their NetFilter components away to eBPF as well, similarly relying on the XDP layer for their load balancing and DDoS mitigation. And also went fully into production in 2018, actually. So yeah, the eBPF community grew, and with that also the features in the kernel. And in order to handle all this incoming kernel patches, Alexei, myself, and David Müller, a networking maintainer, we sat together and basically decided that eBPF has to become its own kernel subsystem. So since then, Alexei and myself, we manage our own Linux kernel trees for BPF and BPF Next, where all the features and fixes land. We have our own mailing list, and we are pushing and collecting all the code that the whole community contributes to BPF and handing that over to David Müller, and he pushes this to Linus Torvalds, who merges it into the upstream kernel. Back in that year, we also worked on eBPF for KTLS. What does it mean? So KTLS is a feature that allows to offload the TLS handling, for example, from OpenSSL into the kernel, and that allows the kernel to also gain visibility. So BPF programs can be attached, and they can introspect the data and then enforce policy. And these days, actually, OpenSSL has it natively integrated, which is great. And in the same year, there was more tools got added for allowing to introspect the kernel about what's going on in BPF land, what programs are loaded, what maps do I have, and therefore BPF tool got added, which is a tool that still gets extended with all the features today. And also in order to ease application development for users, the libbpf was added, which is a C-based library that takes over all the loading of BPF programs so that applications don't have to deal with that because it can get quite complicated. In 2018, Cilium 1.0 was announced, and that basically first brought the BPF revolution to Kubernetes, networking and security. It was added as a CNI plugin in order to integrate into Kubernetes. And it allows for identity-based policies from layer 3 up to layer 7, and also cluster IP services that were handled through BPF and translated there efficiently. A component called BTF, or BPF type format, was added into the kernel. It's basically a metadata format similar to debugging data that we have with Dwarf, but it's significantly smaller in size. And for the first time, the kernel became self-descriptive. What does it mean? From a running kernel, you can actually, it ships its own data format and internal structures, and you can introspect them. And that's basically BTF today is the base for all the future features like compile runs, run everywhere, kernel live patching through BPF, global data handling, and so on. There are many new features being added, and they all rely on the fact that BTF can provide this rich metadata. In 2018, the Linux Plumbers Conference also first got a BPF micro conference. And we also co-organized the networking track, and it got filled almost like half the talks with BPF and XDP topics because it's an exciting feature, and more people are using it and solving problems. And yeah, AFXDP is another socket type in Linux networking that got merged in the same year. And what it basically provides is it provides zero copy for network packets right out of the driver layer, and you can then push them into user space. It's similar to, or it offers a similar feature to what the DBDK toolkit, for example, does, except in the case of DBDK, those network drivers have to be written and maintained in user space. And with AFXDP, you can get the same performance benefits while reusing kernel drivers, so that network device management is much easier, and all that happens at the XDP layer. That's why it's called AFXDP, and the BPF program that can be attached to it allows for steering this into the socket. There's also the BP filter prototype that we've worked on it, and this allowed for translating IP table rules into BPF through a user mode driver. That was basically the first prototype where we can take an existing IP tables binary and generate BPF underneath without the user having to know or realize. Some of those components are used today also for extending the kernel in other areas. In 2018-19, BPF trace first got announced. Next to BCC, BPF trace is basically, those are basically the two main tracing front ends for BPF. Brendan Gregg calls it dtrace 2.0 for Linux because of his capabilities. And it allows, it has a easy to use front end. You don't have to code C programs, you can simply use one-liners efficiently. He also wrote an 880-page thick book on BPF tracing, which is really exciting. It's the first major book on BPF. And Brendan Craig is also working on a new one for 2020 on his second edition of the systems performance, covering large parts with BPF and tracing as well. In that year also, the Cilium 1.6 release actually appeared, and for the first time it was replacing the IP table-based kubeproxy component from Kubernetes through BPF. So all that service handling could be done efficiently. There were many other kernel features added. Some of it, like for the first time, allowed live patching on the kernel from the BPF core infrastructure. It's been used to optimize the data path even more heavily in order to avoid some of the issues that we were seeing from the CPU bugs where red booleans had to be introduced. And it's also the base for several other features, such as BPF trampolines and so on. If you're interested, you should look that up. It's really an exciting topic. There was also the first invitation-only BPF conference among BPF kernel experts to exchange and discuss issues and features. And that's basically from the community side, alternating with the Linux Plumbers conference on a half-year cadence. The BPF backend for GCC finally got merged as well. So both GCC and LVM, the two major compiler suites, have BPF backend support eventually. And in coming more to the present, there's still like a relentless growth on the whole BPF community and features, and we are seeing a third major direction in BPF. So next to networking and tracing, it's also ramping up on security. So Google upstreamed their BPF LSM Linux security module support that they're using in their server fleet. And aside from that, also, that was basically 2019 was basically the year of all the CPU bugs. So BPF also had to protect against Spectre. And that's actually quite interesting because the BPF verifier does a lot of work, sometimes even more work, analyzing the programs than compilers do. And here it even goes into analyzing the safety of speculative program paths. Then on the XDP land, there was a major milestone in terms of cloud providers because AWS and Azure finally had XDP support for the networking drivers. And that actually allows for easy consumption for XDP for the masses because it's super easy to just create node instances with accelerated networking, and then you can use XDP on top of that. One of those users that can actually benefit as well is Cilium, because in the 1.8 release, it added XDP-based service load balancing for Kubernetes in order to efficiently use the CPU for networking in a better way compared to the NetFilter-based approach for kubeproxy. On the kernel side, many other interesting events happened here in that year. Facebook, for example, added a BPF-based TCP congestion control module that allows for experimentation for the data centers to quickly deploy and add new features for the congestion control in TCP. And also Microsoft, they converted their Windows monitoring tools, which are called Sysmon, over to Linux based on BPF. What you can see here is a tweet from the Microsoft Azure CTO that is announcing it. So yeah, like in those few years, it's actually interesting to observe this tremendous change in the Linux kernel, and people are calling it one of the major OS changes in the last 50 years. And Brendan Craig actually says it's one of the biggest operating system changes that he has seen in his career, and is thrilling to be part of it. I can only agree with that. eBPF in numbers. So basically the kernel community today, if you look at how many patches have been contributed, it's around 5,000 patches that went into the BPF subsystem by around 350 contributors, which is quite nice to have such a large community. These days, there are on average every day around 50 new emails on the BPF kernel mailing list every day from Monday to Sunday. And around 4 patches on the BPF kernel subsystems are applied by Alexei and myself. There are many different program types and maps, but the interesting part is on the Linux kernel that the BPF subsystem has over 3,500 test cases. Usually kernel developers are not that good in writing unit tests or self-tests, but BPF is one of the most tested subsystems these days. And aside from Alexei and myself as kernel maintainers for BPF, there are also a team of 6 other core reviewers and major contributors that help with the patch load that is coming at us. And they're from the companies Israel and Facebook and Google. And yeah, overall, it's one of the fastest growing subsystems in the Linux kernel. So yeah, it's like you can see it as an sort of an industry shift, and you have those major adapters, Facebook running it for their layer 4 load balancer and DDoS protection, as well as tracing basically everywhere. Netflix, similarly, where we have a user on the tracing side for BPF. The Google, you have it in running on Android phone devices, but also using it in their server fleet for security and various other aspects. Cloudflare for their load balancing, DDoS mitigation. And there are also a lot of large-scale Cilium users that are running it in production. And if you look at one of the former NetFilter maintainers, Rusty Russell, what he actually has to say about BPF, it's quite interesting. He says, like, you know, IP tables performance used to be mostly good enough back then, but replacing it has taken so long because it required a radically different approach. And it's nice to see it finally happening in BPF. So how can you bring this eBPF revolution to Kubernetes? Well, basically, BPF is becoming ubiquitous these days, as I mentioned. And if you're still relying on IP tables and you have to fiddle around and debug with a large number of rules that are installed by kubeproxy to handle services, well, there's a way out of it. You can basically replace the kubeproxy component as one example with BPF. How is it done? So basically, the way that Cilium is handling services and the load balancing of services, its architecture basically consists of 2 major components. One is to run BPF programs at the socket layer, and one is to run BPF programs at the XDP and TC layer. So let's dive right in. At the socket layer, this is basically for handling all the east-west traffic among Cilium managed nodes. So it's doing the service IP port to the backend translation at the socket. So whenever applications call connect, send message, receive message hooks, it will basically translate the actual request into the backend. And the interesting thing here is that for this, no expensive packet level network address translation is required, because at that syscall time, the packet hasn't even been created. So what basically the BPF program here is doing, it's telling the kernel that the application is actually connecting directly to the backend, whereas the application is thinking it's connecting to the service IP. And the BPF program has both of these contexts and knows what to do with it. And that allows for efficient service handling for the east-west case. Then there's also the north-south case, where external traffic from outside world is basically coming onto the node. And that's handled through BPF programs at the XDP and TC layer. What does it mean? So basically, it's doing the same service IP port to the backend translation on the network driver layer. And in case backends are on a remote node, not on the local one, they have to be pushed back out of the node again. So similar as I showed you in the previous packet flow diagram. And what we've implemented here is basically a SNAT handling with native BPF. And this functionality can basically be compiled into for XDP as well as for the TC layer. And on the XDP layer, as mentioned, allows for high performance and low overhead load balancing. You can use those CPU cycles that you would otherwise have to use to handle the service translation in kubeproxy. You can use those for user workloads instead. That's how it should be. So basically the main principle here is to operate as close as possible to the socket for the east-west case and as close as possible to the driver for the north-south case. So how does it look in numbers? We did a performance comparison on XDP and eBPF as well as kubeproxy. So we had basically 2 bare metal nodes, and we pushed from one node to another as many packets as possible with the packet generator. So you got a load of 10 million packets per second, and we looked at how much those different systems, so BPF versus kubeproxy, would be able to handle under this load. So on those dark blue colored bars, you can see how many packets it was able to handle. In the XDP and BPF case, there were basically 0 drops, and all the packets that were generated from the other node were basically being pushed out to the remote backend when the service is basically on the Kubernetes node remote. And in the TC layer that Cilium is able to attach as well, you were still able to handle around 3.5 million packets per second, whereas the kubeproxy, there's still much more overhead because the net filter layer comes later in the stack than the TC layer, and it was only able to handle around 2.3 million packets per second. And IPVS even has slightly more overhead for just a small number of servers that was tested here than the IP tables one. In terms of CPU capacity, how does it look here? So we were generating a medium load to the Kubernetes node that is under test with the packet generator, and we tested it under 1 million packets per second, 2 million packets per second, and 4 million packets per second. And what you can see here in those bars are the free CPU capacity that can be used for applications instead. Under XDP, it is the most efficient way to handle Kubernetes services. What you can see here is that the kernel spent the least overhead from all the other solutions, because the BPF program here is executed right at the driver layer without having to push it up into the stack. The kubeproxy in the IP tables and IPVS configuration, there was a lot of CPU spent to handle the software interrupt load here. So yeah, how does it look eBPF and Kubernetes in the long future? So you can think of the Linux kernel becoming turning slowly into a BPF powered microkernel. That's actually a really interesting thought here. What you can think of in the long future, that there's just a tiny core kernel with the base functionality that is needed to boot it and to keep things running. But all the other stuff is around that kernel is basically defined through BPF functionality instead of kernel modules, for example. That allows to reduce the attack surface because you have a tiny core kernel. And at the same time, all this BPF code that is defined around it is safety verified to the verifier. And you can get rid of all the feature creep that is otherwise still in the kernel, but you're not going to use it. And you can make a much better use of the CPU resource. So you can think of like that potentially in the long term, Kubernetes could even ship custom kernel extensions that it would need depending on the underlying workload that it has, whether it's running on a data center or on a small embedded system. You can think of the kubeproxy replacement that I mentioned here as one example where BPF can help just as a tiny dot in that universe of possibilities. So with that said, yeah, please go and try out the kubeproxy free mode. And if you can also take a look at the code and help contribute. And with that, I'm opening up for questions. Thanks a lot.